Here's a demo of what the gameplay would look like. First, the game would present the player with a screen, telling them that if they hit the enter key, the game will begin. The score would read above like so, and the lives read in red on the top right here. As the game begins, the current word that is meant to be typed sits on top of the screen. As the player types the word from left to right, the letters would light up green to indicate that they have to type the next letter. Upon completing the word, the underneath would go into place where the completed word was just as a gray color, as is currently untyped. The player will continue playing through until they have lost their 3 lives. With every error, their life counter would drop. When they reach 0, it would send the player to a game over screen, as so. The game over screen would sit here for 5 seconds, holding the final score in the green at the top. After 5 seconds, the player would be sent back to the starting screen. And when they hit enter, it would load up a new game.
So here's a demonstration of the keyboard functionality. The rightmost LED, which is currently on, represents the key released input, which should be high until a key gets depressed, and then go back high once the key is released. So the leftmost LEDs correspond to the keystroke code. We numbered all the letters 1 through 26 based on alphabetical order for simplicity. So if I hold down A, everything goes off, and then when I release A, KR goes high, but all the keystroke LEDs stay low, as A's key code is 0. If I were to hit B, we'd get a keystroke of 1. And then if we hit enter, all the LEDs go high because that is the reset signal to trigger a new game. Another functionality is no matter what other keys I press besides letters, they all output the same thing, and that's to represent an incorrect keystroke that wasn't a letter, which would still mark the user as wrong.
One of the interesting components of our type racer game is the words per minute logic. We use a stopwatch module as well as a double dabble module in order to convert our bits into something transmittable to 7-segment display. We use the stopwatch module, counts clock cycles in order to keep the time while the user is actively playing, and once the user loses, the signal that tells the stopwatch to start goes low, latching the current time. That time can also be reset using the reset signal. As you can see, I've labeled out our switch arrangements for demo purposes. Normally these signals would come from the top module themselves, but for demo, we are manipulating them manually. Currently, I have the total words bound to these 11 switches right here in between my fingers. And with these 3 switches high, we use, with these 3 switches high, that means that total words currently has a value of 7. So if I assert the start signal and start the stopwatch, you should see the LEDs that represent the total seconds light up, as well as the 7 segments start to react accordingly to the words per minute.
Here is a Python script that we made to take any list of 4-letter words that we choose and convert them into our personal 20-bit encoding scheme. So we go through every single word in our text file initially, and then run them through a Python dictionary, which contains for each letter as a key the 5-bit encoding scheme with A as 0 and Z as 25 in 5-bit binary. And then we store them in a separate text file, which we then hardcode into memory. This is our VGA module, which we use to track which pixel is currently colored on the screen. Here we have some parameters instantiated, such as width, length, the base positions of certain letters, as well as the base positions of the scores. We set these letter red, green, and blue registers to affect the color of any given letter depending on where we are in typing the word. Here, the state word position is used to see where we are in typing the word, and depending on what position we are at, we set the letter red, blue, and green registers corresponding with their word position to be a certain color. For instance, when no letters have been typed, we set everything to be gray, as well as the score. To draw certain pixels in certain positions, we check these base positions and the widths and the lengths, as I previously mentioned, to see if a pixel is within a certain box or one of the segments on our 16 segment display. And if that's the case, and if the letter code itself, which is a 16-bit encoding of which segments turn on for any given letter, if that happens to be on for the given position in the encoding, we set the VGA red, blue, and green to be the color corresponding with the given letters red, blue, and green, which we set earlier depending on word position. We do a very similar thing here with the lives and the score, although it's only a 7 segment for the numbers compared to the 16 segment for the letters.
Here's a look into the parts of our project that handle calculating and displaying the words per minute. In order to calculate words per minute, we use a stopwatch module. This module outputs minutes, the tens place of seconds, the ones place of seconds, and tenths of a second. We take this output and we turn it into total seconds. And we use that value to calculate words per minute using 2 separate registers for the integer and decimal portions of the value. Because of the way the 7-segment display works, having the values in this format is pretty useless. Therefore, we run those numbers through a double dabble algorithm, which converts them from binary to binary coded decimal. We found inspiration for the double dabble algorithm online, but we had to alter it to fit our specific bit widths. Finally, once we convert the words per minute from binary to binary coded decimal, we send the signal to a 7-segment control module. Based on the values of the digits of the different digits of the words per minute in binary coded decimal, we light up specific anodes and cathodes of the 7-segment display to show the user's words per minute. We learned how to create this stopwatch module from Simple FPGA's blog post to code a stopwatch in Verilog. This module tracks the time by using a ticker register to count sets of 10 million clock cycles, as you can see right here. Once 10 million is hit, the circuit asserts the click signal right here to tell the system to increment the time registers. One addition we made to this module is latching the time registers when the clock stops so that they can be read later on. We do this by using a state variable for the start signal.
This is our player activity module. This module functions as a finite state machine in order to cycle through the letters we are checking of the supplied word. Starts in state 5, and we go through a boot sequence in order to produce 2 positive edges of word complete. This boot sequence is from 5, waiting for enter to be hit, which is this, to 6, to 7, to 8. We cycle on every positive edge of the clock. We need 2 positive edges of word complete because of this module, which is instantiated here, word library. Word library utilizes a linear feedback shift register to produce a random number or random address on this hard-coded array of words. This hard-coded array of words was produced by a Python script. So the reason why we needed 2 word complete positive edges is because first, on every positive edge of word complete, next word is produced using the random location produced by the RNG, and current word is then put to the next word, meaning at the first positive edge, we produce next word. On the second positive edge, we then produce current word for the user to type through. Once that boot sequence is completed, we go to state 0, which is checking the first letter. Upon a key being released, so a letter being typed, in each of states 0 through 3, each corresponding to a letter of the current word being checked, that keystroke is then checked. Sorry, I'm scrolling around a lot. All right, I'm settling. Upon each key release, that keystroke is checked with the current letter, which we parameterize here with these wires. So, upon each letter, if you get it right, you progress to the next state. If you get it wrong, your lives decrement. And if you do not have any lives left, then you're put into the fail state, which is state 5. Once the user cycles through all of these states, they arrive at state 3. If the user types the correct letter, which is the last letter in state 3, they receive an increment on their score and another word through this word complete. I'm now going to talk about the waveform. This waveform displays the 2 positive edges of word complete, and then this waveform displays the start keystroke, which is 1F, which is equal to 5 ones, which then takes the current state from state 5 through the boot sequence to state 0. Each keystroke is programmed in the test bench to be correct, so we go from 0 to 1 to 2 to 3 without losing any lives, and then incrementing our score to 1. We then are going to lose. So in state 0, you can see lives decrement from 3 to 2 to 1, and once that final life is lost, we go to state 5, our fail state. Now key release is going back up to 1F, which as I mentioned is 5 bits of 1, which will then return the state machine back to state 0 with a new current word. As you can see, all of these words up here are randomized and next word becomes current word. Unfortunately, although this works in simulation, we received a NetDriver error in implementation. This was because in order to display two words, we needed to run next state on both the positive edge of the clock and the positive edge of key release, which could not work.
The functionality of the keyboard starts with the PS2 receiver module, which takes in data 1 bit at a time from the built-in USB to PS2 converter. This data is then sent to the receive key module, which segregates it by use. So the 8 least significant bits are used to represent the most recent keystroke, and bits 15 to 12 represent whether or not that key is being depressed or if it's been released. If it's been released, then the KR output goes high and tells the game logic to check if the expected input matched the actual input. And we're able to do this by using the key code decoder. This module has the same library used to form all of the words, so we could do a one-to-one comparison of the bit streams. Another interesting module is the segment decoder. The segment decoder decides how to drive the inputs on the VGA screen. So the segment decoder takes in data from the current character. The segment decoder is called once per character. It takes this character in and decides how this character should be represented on the VGA screen. So we use a modified 16 segment display to avoid the use of any diagonals or sprites. This saves memory and makes the code more dynamic. By using the modified 16 segment display, all letters are clearly visible without diagonals.